realized that the gene annotation is a little tricky, so I'm going to go through it right now and try to clarify and hopefully explain how to translate between these different coordinate systems. So the protein, which is amino acids, has a coordinate system with amino acid number 1 being methionine, and it goes to amino acid 625. Then we're going to go to the CDS, which is the coding sequence. And so since it's coding sequence, it starts with ATG, okay, which is a nucleotide number 1. So now CDS being DNA, or representing the RNA, it is in nucleotides or base pairs. So nucleotide number 1 is A for the start of the start codon, which is ATG. And in the end of the stop codon, ATGA, is nucleotide 1878. Then once we get this, these regions mapped onto the CDS, I'm going to then map them onto the genomic DNA and also map the splice junction back onto the CDS. Okay, so let's get started. So let me demonstrate, as we discussed in class, to go from protein and amino acids to CDS, we multiply by 3 because there's 3 base pairs and a codon. So when we start, let's say, with position 1, methionine, which is our start amino acid, that's the first amino acid. So then what I would do is 1 times 3 equals 3, obviously. Okay, and then to find the beginning of the codon, so there's position 3. Okay, so that's the G. And so that's the codon, 1, 2, 3. So then if I subtract 2 equals 1, that gives me the 1, 2, 3. So 1, 2, 3 for my start codon right there. Okay, ATG is 1, 2, 3. Okay, so that's the ATG codon, or methionine. Oops. So this is methionine to ATG. Okay, now let's just do one more example since 1 is kind of hard. So this is position number 3. So we have M methionine, K for lysine, and N for asparagine. So position number 3 is asparagine. So let's do that one. So asparagine is into the codon. So what is the codon? So the codon is going to be position amino acid 3 times 3 equals 9. Okay, and so there's that codon right there. Sorry, that's the position of the codon. 9, that's the third base. So if we subtract 2, we get 7. Okay, so we know that that N is codon, is nucleotides 7, 8, 9. Okay, and so down here would be our codon, 7, 8, 9. So that's how you calculate the codons based on amino acid position. So let's do it here for the transmembrane domain. So transmembrane domain, we're abbreviating TM, is, the start is 244, so I multiply that by 3, and that equals, do this with a calculator so I don't make mistakes, 244 times 3 is 732. Okay, so that's the last position for that amino acid. So then we minus 2, so we get 730. Okay, so we know that the start of that codon is nucleotide number 730. Okay, so I go over here, and I'm going to draw, let's draw a little oval. Okay, so we're going to draw a little oval. Alright, let's color it the green so that I have a consistent color scheme. And so that position is going to be 730, okay. 730, okay. Let's do something. So we have our TM, which is 732. Okay, so that was that. So that's 730 to 733 would be the codon. And so the end of the TM, so this is TM start. And then TM end is, let's do beginning. And the end, of course, is the same thing. 266 times 3 equals 798. Okay, minus 2 equals 796. Okay, so our it's 796 nucleotides to 798 is the codon represented by this amino acid right here, 266. So let me put that in here. So 798 is our end of that codon. Okay, good. And then we do repeat for the kinase. So let me draw in a box for the kinase. Let's just do it like this for now. And so let's make it the pinkish color there. And so what are we going to do? So for the kinase, the same thing. Kinase begin is 343. Okay, times 3 equals 1029. And so minus 2 equals 1027. So 1027 to 1029 is that nucleotide, is that codon, okay? And so let's do the end. Is 3613. So times 3 equals 948. Okay, minus 2 equals 946 to 948. Base pairs or nucleotides is the position there. So let's go over here. But something doesn't make sense. So if you notice, I made a mistake because I just realized something doesn't make sense, because the beginning is at 1029, but I calculated this would be the end is before the beginning, and it looked, and I entered it wrong in my calculator. Times 3 is 18. Is 1839 minus 2 is 1837, and so that goes to 1839. Okay, so there. So again, always asking yourself, does that make sense? And it didn't make sense, right? So I had to fix it, because we know something about the biological sequence, so we can decide if things make sense or not. So this is going to be our range for the kinase domain. Okay, so there we go. And let's then pick this up, and we can put it and we'll put it right there. And we're going to move this a little bit because it's not that close. This doesn't have to be to scale, but it should make sense. And this needs to be just a little shorter or moved over just a touch. If I can do that. There. Like that. Okay. So that's what we've done. So I've said that the start of this codon for this amino acid is 21027. And then this amino acid, we need the end codon, the end nucleotide, so that's 1839. And it fits within our CDS because CDS is 1878 nucleotides long, and this number is less than that number. So that's good. The 1839 is less than 1878. So that's good. Everything makes sense. Okay, now let's go to our gDNA. So if you need, you can, this is an example, and then if you need, rewatch this part a little bit, a few times if you need to figure this out more. Okay, now what we need to do is we need to find the location of these exon boundaries in the CDS, because we need to know relative to the transmembrane domain. So is the transmembrane domain here or here? Okay, we know the kinase is down here somewhere. Okay, we know it's in this exon because of the numbering, I would assume. And then, but this we don't know. We can't really calculate it easily to know whether it belongs in this exon and this exon, or if it spans. You know, it could be a little bit here and a little bit there. So now what we're going to do is use information from TAIR to annotate this gDNA, and then we will go then we will be able to find that location. So what I'm going to do is go full screen there and do the little click to get my view sequence. So now I can highlight up all the things, and so what I want is I want exons. Let's see, let's go with UTR. So the UTR is going to be position 1 to 2080, 2079, 78. 78. 278. Okay, so 1 to 278 is that UTR. And then we go to 21, 31. Well, that's going to be 31. So that's 40, 39. So 2339 to the end, which is 20260123. Okay, so there's my UTRs. Now let's grab our exons, undo that. Our exon is going to be 1 to 15, 6, 1, 2, 3. So that's exon 1. And then exon 2 is going to be, oh, we have 3 exons. Is that what I have over here? Yeah, 3 exons. So then this is exon 2 is going to be 41, 51, 52, 53, 16, 53, 2, 1970. And exon 3 is going to be, it's 41, 51, 61, 2, 3, 4, 2064 to the end, which we said was 2603. So what I've done is just done on a piece of paper, wrote down those numbers. Now I can go and put them onto my drawing. So here we have 1 to 278 is going to be UTR. So let's grab a rectangle. Let's make a UTR like that. We'll put it something like this. And let's give it yellow. And then we got one at the other end, so let's do that. We have 2 UTRs, the beginning, the 5 prime UTR, and that's position 1. It's position 1 to 278. Okay. There, that's our UTR. Now, okay, now what's the end point? So the 278. So our ATG, let's copy that. Okay, we'll do it another way. So our ATG is like that. And that would be position 279. Right, so 279 is the position of the A in the ATG. So that's the start of my exon, and the end of the exon is exon 1, 1563. There, that's the end. Okay, now just copy and paste that. Exon 2 is going to be exon 2 is 1653, and we're going to 1970. Okay, and finally, we're going to go from here, which is 2064 to 2603. Oh, I need the stop position of the stop though. So where is the stop? Let's go back. Open this thing again. Where's my start? There's start. 281. Yep, 278 was correct, and then the stop. The stop is going to be it's 21, 31, 2, 3, 4, 5, 6, 7, 8, 2, 3, 3, 8. 2, 3, 3, 8 is stop. Okay, is that right? 1, 2, 3, 4, 5. No. Yeah, 1, 2, 3, 4, 5, 6. 2, 3, 3, 6 is the stop. Okay, so let's go back over here. Two, 3, 3, 6 is stop, and then the end of our gene is 2603. There. Okay, and we will put in our stop. And I did check, it is TGA, so that's our stop codon. There. Now we've got our gene annotated. Now we can put the location of the exons onto our CDS. So I'm going to just slide this over a bit so that it's centered a little. Okay, so the first exon, okay, so remember, coding sequence is only coding sequence, ATG to TGA. So the yellow is not present. So what I'm going to do now is translate or go from this coordinate system where 1 is way out here and ATG is nucleotide 279, I've got to go to make ATG 1. Okay, so this coordinate system, 1 starts at the beginning of the gene, and in this coordinate system, 1 starts at the A of the ATG. Okay, so then if that's 1, this is now 1. The end of this exon is the length between the ATG and the end, right? So to calculate that, so exon 1, right, is going to be exon 1 is going to be 279 minus 1563, okay, and that equals 297. Of course, this should be negative, but I'm not going to make it negative. And then to be exact, we need to add 1. Okay, why do we do that? Now, here's an example. Here's a series of numbers. Now, here's a series of letters. Okay, so we have 1, 2, 3, 4, 5, 6, 7 letters. So how many letters do I have? Okay, if this is position 1 and this is position 7, if I subtract 7 from 1, I get 6. So I have to add 1 so that I get the exact number of letters that we have. So example, let's say so what if I want to know how many letters are in this one? Okay, obviously we can count, but let's do it by numbers. So 1, 2, 3, 4, 5, 6, 7. So this R is position 8. Okay, so 8, R equals 8, and then we go to 8, 9, 10, 11, 12, 13, 14. So S is 14. So if we do 14 minus 8, that equals 6. But we know that but if we go back and count, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, 11, 12, 13, 13. 13 minus 8 is 5, right? But we know that there are 6 letters here. So we have to add 1 in order to get it to be precise. Equals 6. Okay? So for exon 1, we have the length is nucleotide 1563 minus the start codon, the A of the start codon, which is 297. Okay, that gives us 1226 plus 1 is 1267. Okay, and so the end here is going to be at 1268 because it's add 2. Because you get 1 here and then between here and here, so you have, actually that's overkill, so forget that for now because we're adding it to 1 here, so it is 267 there. And if you don't do the plus 1s, it's okay. So now you can see already, so that's this position. Okay, so what I did is I calculated where the intron was. Boom. Okay. So I calculated where the intron was in this before splicing. Okay, so after splicing, these 2 exons are put together, and so this is the position. This is the exon-exon junction at 1267. There. So that's the position right there. Now you can see why I did this. Oh. Okay, so now you can see why I did this. See, this number is bigger than this number. These numbers are smaller than this number. So the transmembrane domain actually belongs over here. Okay, that's why I did that. And then this position is easy to calculate. So exon 2, right, is this difference here, 1970 minus 1653, and that's going to give us 317 317, and so we're going to add 317 to that number. So we're going to add 317 to 2267 because that's exon 1, exon 2 boundary. So then that's going to be plus 2. So this new exon position is 1584. Okay, so actually it needs to go quite a ways. Not that far. Okay, and then so that equals 1584. Okay, and so that's this position. Let's say, let's put it right about here. Like that. Okay, in mine actually it splits the kinase domain. Okay, so it splits the kinase domain, so let's just make this a little bit bigger here. There we go. Actually a lot bigger. So it actually spans most of these, so we'll do that. So my protein that I chose is going to be a little different than yours. Okay, but there we go. And then my other region, we'll call it here. And notice this is not to scale. Okay, and so there's my exon 2, exon 3 boundary right there. There. So now I know we have, this is exon 1, then after splicing, this is exon 2, and then after splicing, exon 3. And then I calculated just based on the length and adjusting this 279 becomes 1. So then this position is the difference, or subtract this from that and add it to 1 and you get that. Then you subtract this from that and add it and you get that position here. And that gives us our second exon end and the start of the third exon and the rest of the CDS. So there you go. That's how you can do between these three different coordinate systems. Amino acid, nucleotides, in the CDS where we have no non-coding, right? This is all coding, and here we have non-coding and coding sequence. Okay? So that's what you have to keep in mind. Now, in some cases, now the challenge for you is how do you go from here? How do I put 738 to 789? How do I change this coordinate to the coordinates where now 1 is at the UTR and you want to put the location of the transmembrane domain? So I'll do one example. Okay, so we have more sequence, right? So we have more sequence here. So 1 is now over here, whereas before it was 279. So we just simply add 279 to these two numbers. So, so this is for CDS. This is gDNA to CDS. Okay. Now we're going to go CDS to gDNA. Okay, this is the transmembrane domain. So 730 plus 279 equals 1009. Okay, so 1009 here. to what are we going to have down here? The stop is going to be at end is 798 plus 279 equals 1077. So let's go up here now. There. Now I've changed the coordinates from the cDNA, sorry, the CDS to the genomic DNA. Now, to get these, I'm going to have to actually include potentially the intron and the intron. Yours is going to be much simpler. Okay, so yours, everybody's that I've seen, if you have an intron, the kinase domain is only in this exon. Okay, so I'm going to modify mine to do that. So I'm going to change this number to 1600. Okay, so I'm making this up now, but this is so it will look more like what you're going to see. Okay, we'll come back and deal with those. There. And so the exon boundary, let's just move this so that it is all relative correctly. There. So now this is the exon 2, exon 3 junction. Okay, let's just do this. It's going to look a little wacky, like that. Like that. There we go. So this is what yours is going to look like. So ignore this number. Let me modify this. Okay, that has to be a multiple of 3. So this now becomes 550. There. So what I'm creating an artificial situation, but this is how yours is going to be. And so now what we need to do is map this onto our exon. And we know that it's in the 3rd exon because of the coordinates. So we know it's going to be down here. Okay, so let me copy and paste it where it belongs. There we go, somewhere like that. Okay, gonna have to shrink it a bit. And you can play with your diagrams so that they have a little bit more sense, but there we go. Now we got to change these two numbers. Okay, So how do we do that? Well, we have more non-coding sequence. So before, we just had to add 279 because that's how long the UTR is, plus the ATG. So we added 279 and got these numbers to these numbers to do that. But now we also have the non-coding RNA introns 1 and 2 that we need to fit, that we have to worry about now. So to do that, I'm just giving myself some more room. Now, there we go. So now we've got to calculate the start and stop of this, but we've got to include the introns. So we need to calculate one length of intron 1 is equal to here 1652. That's 1653 is the start of the exon, so the end of the intron is 1652. And then we do, this one is 1563, that's the last nucleotide of the exon, so the first nucleotide is 1564. And that equals '88, the small intron there, so it's 88 nucleotides, and the length of intron 2 is the same thing, so it's going to be 2063 minus 1971. It's 92 base pairs, another small intron. Okay, so the total intron, so then, let's go through that. So then this number is going to be, so kinase start, it's going to be equal to 1650 plus 279 plus intron 1, 88, plus intron 2, 92. Okay? Then that's going to be what? 1650 plus 279 plus 88 plus 92 is 2109. Okay, so this number is 2109. In the same logic, we're going to do this. According to the same logic, what we're going to do is the kinase stop. Oops. The kinase stop is going to be 1839 plus the UTR plus the intron 1 plus the length of intron 2, and so that's going to give us 2298. Okay, 2298. There. That's how you do that. That's how you translate between these different coordinate systems, or convert between the different coordinate systems. Now, you need to, and you have to sit down and really think through this, right? These are amino acids. All of this is amino acid. Even the line is amino acids. There's 625, and it starts at position 1 with methionine. The CDS is position 1 is ATG, which is the codon for methionine. But the cDNA, but the genomic DNA has non-coding sequence. And so you have to sit down and think about all of these different things when you're trying to design your experiment. If we didn't know where this transmembrane domain is, if we needed to know, because we need to know where it is relative to the exon-exon boundary. Okay, is it in exon 1, and exon 2, and exon 3? So we had to calculate the boundaries for our CDS. the exon-exon junctions for the CDS, and then we could place our TM in the proper spot. Then we had to coordinate. We had to change coordinates again when we went from CDS to genomic DNA so that we could place the kinase in the proper place. Okay? And some of these numbers might be slightly off, like this possibly should have been 278. Now that I think about it, it doesn't matter because these are all predictions anyway. Okay, so 1 or 2 nucleotides is not going to be a problem because when we design our guides, we're not going to do it right up against the boundary, right? We're going to design the guides slightly to one side or the other. So if these nucleotide numbers are off by 1 or 2, it's okay. We have the relative position, and that's what we really need, okay? And also when we design our guides, I mean, we might even have to pick a guide here to target this region. We got to be aware that we've got to pick it in exon, not in intron. Okay, so there you go. That's how you do this. I hope it clarified things, and if not, again, ask during office hours. And but I think if you sit down and go through this on your own with your specific gene, that you will be able to figure this out. Okay. And if you think really carefully throughout the whole course, this is really a good summary of everything we've talked about up until now with genetic information transfer. Okay, really forcing you to use all the biological concepts, in this case for primer design and guide RNA design, but in other cases it could be for to learn something about the gene itself. Okay, good luck and have fun.